Hello and welcome to my new lecture. In this lecture, I would be talking about heat absorption, heat absorption in solid, liquids, and gases. Like we would be defining terms, heat capacity, specific heat, and molar specific heat. Then we would come towards heats of transformation, and later on in this lecture, I would be stressing on the relationship between the work done and the heat energy that is transferred into or out of the system with different types of graphs and what meaning they convey. Before starting this lecture, I hope that all of you students know the zeroth law of thermodynamics and what are temperature scales like Celsius, Fahrenheit, and Kelvin scale for temperature measurement, and what is actually meaning of temperature and heat. Heat is basically transferred due to temperature difference. Let's start our discussion with the topic is 18.8 of Halliday Walker's book Fundamentals of Physics, and it is absorption of heat by solids and liquids. Okay, first of all, I would define the term heat capacity. Basically, heat capacity of a material is proportional to its mass heat capacity is proportionality constant between the heat Q that the object absorbs or loses and the resulting temperature delta T of the object. So it is a relationship between Q, that is heat, that is heat energy absorbed or lost by a material, and delta T, where C is the heat capacity that is proportionality constant between them. And you can see the C would come out to be the ratio of amount of heat energy per unit change in temperature. And let's say if the temperature changes from some final temperature to minus some initial temperature, then we can go back to the relationship and see that it would be equal to C times final temperature minus initial temperature. This specific heat is inversely proportional to heat capacity is inversely proportional to change in temperature and directly proportional to amount of heat energy. Okay, one thing confusing is the capacity associated with that heat. At times people take the meaning of capacity is the, let's say, ability of the bucket to hold water. It would known as it heats capacity, but it is not like that. Heat capacity means that ratio of amount of heat energy to change in temperature. Its unit could be let's say energy is in joule, and let's say temperature is in Kelvin, then the unit would be joule per Kelvin. Or it could be if the amount of heat energy is in terms of calories, then it would be calories per Kelvin. Next, the term is specific heat. Specific heat basically includes the masses in it, and we slightly change the relationship that we discussed in let's say in equation A. Suppose there are two pieces of marble with different masses, so they might have different heat capacities. So it is better to represent the materials in terms of their specific heat. So specific heat is given by the relation Q is equals to C times mass times delta T, where delta T, let's say, changes from some final to initial temperature. Then this relation would be given like this. Let's call this as equation B. In table 18.3 of the book, the specific heats at room temperature of different elements like lead, tungsten, silver, mercury, ethyl alcohol, seawater, water, etc. are given. And just for mention, the specific heat for the water is 1 calorie per gram centigrade. As you can see, to define specific heat, C would be equals to Q over M times delta T. So one can see that its units are like Q is in calorie and mass in gram or kilogram, and temperature is in let's say Kelvin. Then its unit could be calorie per kg per Kelvin. And the specific heat of water is 1 calorie per gram per centimeter, and it is equals to 4180 joule per kg per Kelvin. So if you want to use it in numericals, you can take this value of specific heat of water, and same many other elements specific heat is given in table 18.3. Often it is convenient to represent the amount of substance in terms of number of moles. So to include this, we would have molar specific heat, and we know that number of 1 mole of a substance has 6.023 into 10 raised to power 23 atoms 1 mole of a substance contains. And when you have material in terms of number of moles, then the specific heat will be in terms would be as molar specific heat, and specific heat unit would become as, say, Q is in joule over let's say the substance mass now replaces by number of moles, and temperature is in Kelvin. So this would be our unit for molar specific heat. And same table 18.3 also has molar specific heat of different substances. Now, as the matter exists in 3 states, solid, liquid and gas, molar specific heat for solids and liquids do not change much, and we calculate basically the molar specific heat at let's say constant volume and or at constant pressure. However, this is the case for solids and liquids, that molar specific heat changes very little, by a few percents, and in case of gases, this molar specific heat changes quite large in case of at constant volume or at constant pressure. It is noteworthy that when energy is absorbed as heat by a solid or liquid, the temperature of the sample does not necessarily rise. It doesn't rises. However, the state or the phase may change from one to another. Let's say matter exists in solid, liquid, or gaseous or vapor state, and when we basically add heat or basically extract heat from these substances, that may or may not increase or decrease the temperature, but instead it might change the phase, like solid goes into liquid or liquid goes into vapor. So it is important to note down the heat of transformation. When matter changes its state. As we know that matter exists in three states: solid, liquid, and gaseous, or it is known as vapor state. So in the solids, the molecules of a sample are locked into a fairly rigid structure by their mutual attraction. The solids have got rigid structure, while in the case of liquid, the molecules have more energy and move about more. They may form brief clusters, but the sample doesn't have a rigid structure and may settle into a container. So they do not have rigid structure, but they may form clusters. Solids have rigid structure and liquid doesn't have rigid structure, but they may form clusters. Next is gas. In the gas or vapor state, the molecules have even more energy and are free to move, are free of one another and can fill up the volume of a container. So in gaseous state, the molecules are free to move and they may fill the volume of a container. So to melt a solid into a liquid state, the process requires molecules of the solid must be freed. As we know that in case of solid, the molecules are in rigid state, they are bound together. So to transform them into a liquid, we need to break the rigid structure. So to change the solid to a liquid state, we need to add energy to the system to break these rigid structure. However, if we want to go in reverse order, let's say we want to change the liquid to solid, then we have to basically that the liquid must lose heat so that it changes into a solid structure. The melting and obviously freezing are examples of changing solid to liquid and back from liquid into the solid. Similarly, to change a matter from liquid to gaseous state, we need to break these cluster of the liquid molecules. So once again, energy is required in this case to break the clusters so that the liquid may change into gas or vapor state, and if we want the reverse of it, to change the gaseous or vapor state into liquid state, once again we have to basically remove heat energy from that particular gas, so that it changes into the liquid state. Changing liquid into gaseous is basically known as, I can write it down as vaporizing, and changing gaseous to the liquid state is known as condensing, or process is known as condensation. And similarly, from solid to liquid it is known as melting, and from liquid to solid it is known as freezing. So heat energy, one thing is for sure, that heat energy is required to transform basically the states of matter, and the amount of heat energy that is required to change the state of a particular substance per unit mass is basically equals to L, that is heat of transformation. This is known as heat of transformation. When this transformation is from solid to liquid, we have to basically add heat energy, or it is from liquid to solid. This basically is known as heat of fusion, and it is represented by L sub of capital F, latent heat of fusion. So the relationship that should be Q is equals to L times the mass now becomes, for latent heat of fusion, it basically comes like Q is equals to latent heat of fusion times the mass. And if the transformation is from liquid to gas or vapor state, then obviously we have to add heat, and if we are to change the gas state into liquid state, then we have to basically remove the heat energy. This transformation would result in known as heat of vaporization. And the relation that let's say this is equation C. Now the C for this case becomes Q times latent heat of vaporization times the mass. So these D and E basically are relations when you include latent heat of fusion and latent heat of vaporization. Latent heat of let's talk about water. Latent heat of fusion for water is 333 kilojoule per kg, and latent heat of vaporization for water is 2256 kilojoule per kg. There is a table in the book 18.4, table 18.4, which basically gives melting and boiling point of different elements, and along with their latent heat of fusion and latent heat of vaporization. Now as we are going along, we need to do some numericals as well, and I have taken numerical number 25 that may change from version to version of this book. There are many latest version, and hopefully you can match the statement with your book to actually see the numerical and how to solve it. In most of my lecture I would solve the numericals from the exercise, so the numericals that are solved as examples in book, you can easily solve them by yourself, as they are already solved in the book. In this numerical, the given statement is calculate the minimum amount of energy in joules required to completely melt 130 gram of silver initially at 15 degree centigrade. By given data I have the mass is 130 gram, and I can change it into standard unit by dividing it with 1000, so it would be 1.13 kg. And I need to know the latent, because I want to change it from the solid to liquid state. I have to melt the silver, so I need to know the latent heat of fusion of silver. I can go to the table 18.3 that I told you and check the value of latent heat of fusion of silver, and latent heat of fusion of silver is given as 105. So basically I have to calculate the amount of heat energy, then Q would be latent of heat of fusion times the mass, and 0.13 multiplied by 105 would give me so the result comes out to be 13.65 joule. So this is one of the numerical. Hopefully by using these formulas you can solve many other numericals in this book as well. So in first part of this lecture I have told you about different terms like heat capacity, specific heat, molar specific heat, and heat of transformations. Now I would move to my next section, that is how basically you can look the relationship between heat and work and volume and pressure, and when the work is positive, when work is negative, when heat is added or removed from the system. Similarly, what is constant volume and constant pressure. This would be very useful in understanding the relationship between all these different quantities. Before going into that detail, first I think I should be teaching you about the integral and summation, right? Integration is like summing up, right? It does the same work as you apply the summation, but integration is for a continuous function, and summation is for sum of a discrete system, right? And let's say the variable in case of integration is infinitely small, right? And this is not the case for summation. So you should know first what is the meaning of integration. So integration basically means to add up, and it is for continuous systems. Now in this portion I would like to discuss in detail how energy can be transferred as heat and work between a system and its environment. Let us make a system. Suppose this is a cylinder like this, or a container, and there is a reservoir beneath it where I can basically provide it with heat. Let's say this is some temperature reservoir, and at the top of it, let's say there is a piston, right? This piston can move up or down, and the gas is filled in this container. So I can make changes. I can add heat to the system through temperature, this temperature reservoir. I can maintain constant volume by not disturbing this piston, or not making it to move, and I can maintain constant pressure by adjusting the piston. So it can actually represent different situations that I am looking forward to. Suppose there is some initial states. Let's say the volume at some initial state is Vi, and pressure at some initial state is P sub of I, and temperature, let's say, is T sub of I, and similarly after basically you change, you want to change it to some final volume, final pressure, and final temperature. So this change from its initial state to final state is known as this transformation, or this change is basically a thermodynamic process. During such process, energy may be transferred into the system from thermal reservoir, that is positive heat, or it may be removed from the this reservoir, that would be negative heat, as heat is removed from the system. Also, work can be done by the system to raise the loaded piston, let's say, that is positive work, or lower the piston, that would be negative work, right? If the piston is moved upward, then the work would be positive, and if the piston moves downward, then the work will be negative. We will definitely see all these cases, but let's first derive the relationship. Suppose I allow the piston to move by some, let's say, if I have applied some force F, and the piston has moved through the distance dfs. Now the small amount of work that has been done as the system, as the piston moves upward, would be dw, let's say, that is a small change in work, is equals to let's say force times the displacement. You know that work is equals to F dot D. Since I am taking a differential change in work, that is differential change in displacement. So if I integrate both the sides, this would be dw would integration would come out as work, and that F basically is pressure times the area. Now this area into some side or some displacement would basically represent a change in volume. So this would be pressure times A dot ds would represent differential change in volume as the piston moves upward. So the work done appears to like this. And now the integral is either definite integral or it is indefinite integral. Let's make it as a definite integral, and the integration is on the volume, so it would be some initial volume to some final volume. So this would be my relation. I can write it more clearly as from Vi to Vf, pressure times change in volume. So the work done depends upon the change in volume. It should be clear from this relationship. But when the volume changes, and there can also be change in pressure, or there can be changes in temperature. Next we would look into some PV diagrams, that is between pressure and volume, and how basically they are useful and what sort of meaning they convey about that thermodynamic process. Before going into that, we need to look at another thing, that work done is basically the integration of pressure into change in volume. So integration, one of the meaning of integration, as I told earlier, is about summing up. The other is area under the curve. This work done that is equal to this relationship is same as if you have PV diagram, and area under the curve of that PV diagram would be work. So in the coming up conversation, that would be very helpful. Suppose first, in the first diagram, this is my volume, and along y-axis is pressure. Suppose the system undergoes change like this. This is my initial state, and this is my final state. Now one can see that what would be the work done. As I told earlier, work done is area under the curve of this PV diagram. So the work done would be, all of this is work done. And next thing is, we want to know whether the work done is positive or work done is negative. Whenever the volume of this thermodynamic process increases, the work done would be positive. So in this case, work done would be greater than 0, right? And if the volume increases, in this case you can see that the volume increases but the pressure decreases. And when the pressure is decreasing, what can you say about the temperature of that thermodynamic process? So as the pressure is decreasing, one can say that the temperature has decreased, and this temperature decreasing basically represents the loss of heat of the system. Now let us look, this is my figure A. Now let us look into another figure to understand this briefly. This is my volume and this is pressure along y-axis. Now suppose that system first moves from this initial point to a point. This is at constant pressure, and
then it goes into basically decrease in pressure, or you can say that it goes into constant volume, and this is my final state as I have written it down. So you can divide it into two phases. One is IA at constant pressure, and the second one is IA, and the second one is AF. AF is basically at constant volumes, and IA represents constant pressure. Now in case of IA, as the volume is increasing, as I told before, it means that work has been done and positive work has been done. And when volume increases, basically that is due to the increase in temperature of that system, this means that heat is added to the system, which basically which allows we have allowed the piston to move upward, so maintaining the constant pressure. In order to maintain the constant pressure, we have to basically increase the or move the piston upward, so that the pressure remains constant. In the second part, however, the volume does not change and pressure decreases. This decrease in pressure means that the temperature has decreased and heat is taken out from this, let's say the system we were discussing, that gas filled in a container. So the heat is taken out from the system. As in case of IA, when heat is added to the system, that heat is positive, and in case of AF, when heat is removed from the system, this Q should be negative. So these are some of the indications how basically you can study the PV diagram. And work done is positive because in the first phase work done was increased, and in the second case, since the volume remained constant, so there was no work done, right? Overall the work done was positive. Let me mark this as figure B. Now let's talk about another figure, another PV diagram. This is pressure, this is volume. Suppose initially the system is at constant volume. This is my initial, and this is, let's say, point A, and then basically the volume of the system increases and reaches at my final state. So between I to A there is no change in volume, so there would be no work done, and it means since the pressure is decreasing, you can say that heat is being taken out of this system, and Q would be negative. In case of AF, you can see that there is a change in volume and volume is increasing, so the work done would be positive, and this area under the curve basically represents the work done, and this work done is positive. But this work done, however, is lesser than the work done that we have in case of figure B. So when the gas is expanding or the volume is increasing, it means the temperature is increasing, and you can say that heat is being added to the system. Now another, we are discussing PV diagrams. Let's take another example. Suppose this is my volume axis, this is my pressure axis, and let's say this is my initial point, and I go from this initial point, let's say this is my initial point, to some point, let me call it as C, to some point D, and then to point F, and by taking this path. And you can see that work done in this case would be like this one, right? And suppose I can take another path. I go from this initial point to point G, and this point is H, and then I came back to this F. So there are two paths, one is ICDF and the other one is IGHF. So you can see in this case that you can make the work done by the gas small by choosing the path ICDF, or you can make it large like this by choosing the path IGHF, right? So by looking at this figure, we can say that as the amount of work done is different by following different path, it means that amount of heat energy and the work done that is involved in this system is path dependent. Now looking into another system, in another PV diagram, this is my volume axis, this is my pressure axis. Suppose the system goes from this initial state into this final state. This is my initial state and this is the final state. Now one can see that the volume is in this case is decreasing as you go from initial to final state, and as I told you that work done is equal to area under the curve of this PV diagram. One can see that as the volume is decreasing, this work done in this case would be negative. So as the volume is decreasing, it means at the same time you can see that the pressure increasing. You can say that when the pressure is increasing, heat is being added to the system. It means that Q is positive in this case, right? This is another diagram that could be visualized to study PV curves or relationships. So looking into this figure, let's say it was D and I could name it as E, and this one is F. Looking into figure F, one can say that the gas was compressed into in the container in this case. Now the last PV diagram to show you is of a cyclic process. Volume, pressure, cyclic process. You start from a point, let's say this is my initial point and this is my final point, and you come back to the same point. This is like a cyclic process. So one can see that when I was moving from initial to final state, the work done is more rather than when I was moving from final to initial state. As you can see that area under the curve for this one, initial to final state would be larger than, because this basically this inside this would be whole work that has been done, and this work done, overall net work done would be positive in this case. So all these are different PV diagrams which could be very helpful to understand the pressure volume relationships and work done, and when heat is added and when heat is removed from the system, and constant pressure and constant volume as well. Hopefully you have enjoyed this lecture, and I will come back soon with another lecture related to thermodynamics. Thank you very much, all of you.